Good morning. Good morning, everyone. Thanks for attending this meeting and listening this presentation. Today, I'm going to introduce a topic about modeling mobile traffic patterns using a generative adversarial network. It's based on our short paper for this conference. I'm the first author, Boma, from University of Sheffield and Ramplan Wireless Company, and the other three authors are from Zhejiang University, Ramplan, and University of Sheffield too. And today I'll introduce three parts major. The first part is background and why we need that. Secondly, the method, how we solve the problem. And thirdly, about the results. There is going to be 15 minutes about this presentation. So let's start with the background and our motivation. From the right part of the finger, that's what we're designing in the Ramplan company. We want to simulate some 5G real-world deployment of the base stations. In the previous part, we have no idea about the user distribution. We just modeling the channel condition and something else in building and out of the building. But currently, we find that it's not very efficient to do that because we have no idea where are the users. We cannot distribute the resource where they are required. So we need a real-world user distribution to describe that. Indeed, we can get some data from cellular operators in UK, like Vodafone or some other operators. It can give us some special temporal hotspots. However, the data set is limited, and we would require to expand this limited data set to unlimited. So that's why we need a tool for that. And our requirement, firstly, we need temporal resolution, less than 1 day, like morning, afternoon, midnight, something else. Another one is that spatial resolution should be less than 10 meters of the user distribution. That's what we want. So the literature review about how many tools. When we find some papers about this, we categorize the literature into two kinds. The first one is that they fit the user distribution with probabilistic distribution, like of a stable, ZIP or any other distribution. Probabilistic distribution can be used to fit by optimizing the parameters. These methods rely on maximum likelihood to optimize it. It includes some manual operation of it. It's not very efficient to do that. And then we find another tool of machine learning, which can optimize the parameters by gradient descent. It is called Generative Adversarial Neural Network. It is GAN. That's what we want. And then let's see if they satisfy our requirement. We firstly find that the low spatial resolution is the first gap. What they are using is a cellular data. Cellular data based on the base stations, that's pretty low resolution. They're 235 meters square of one unit in their research. Another one is that the temporal resolution is very low. It's a week-long or month-long research. That's not what we required. And thirdly, it is operator biased. They usually collect one operator's data. As we know that there are a lot of operators, we want to understand the distribution of users. Maybe it can reflect the distribution of all operators. So that's the third gap. And finally, there's no temporal changes 1 day. No correlation, for example, correlation of morning, afternoon, and correlation of morning of Monday with morning of Tuesday. So that's the motivation we need to improve in this site. In this paper, we just design and convincing artificial real-world user distribution generator. and the resolution it can achieved with higher than 10 meter with 10 meter. Yeah, that's a pretty high resolution. And thirdly, the temporal resolution should be higher than 1 day, not 1 week, not month. And there's no operator bias. And we can use the generator to expand limited data set to unlimited data set. That is also useful in semi-unsupervised learning. And also see another paper include this in meeting. So let's see how we design and solve the problem. When we want to solve the problem, we first say that generative adversarial process is important. So firstly, what we want, let's see the mark first. What we need is a generator. From the left side, what the input is a random noise of the coordinates of users. And when it goes through the generator, it can generate a traffic pattern, generate the user distribution. How they did that? They did that based on another thing called discriminator. This discriminator will compare if the generated data is similar to the training data. Training data is the real world data we collect. And then it gives a decision is real or fake and compare the loss. So that's the third thing. And then the loss will be feedback to generator. That's a process. So what we need to do, because the generative process is already there, yeah, you can directly use it and use their experience to train your model. And what we need to do, and our contribution is firstly, we need to prepare the data, the pre-processing, as we know that there is still no work to improve the resolution to such a high level, and how to reduce the noise, how to improve the accuracy. That's a problem. And thirdly, we need to define a loss function or a similarity function. It is to say that how to compare the two generated and trained data, they are similar to each other. If they are not similar, how we measure or quantify the loss, that's a problem. So firstly, let's say the data. We collect the data from Twitter because the Twitter has exactly the GPS location of users, and the resolution is less than 10 meters. But as we know that only part of or a little part of users in Twitter share their locations, and then not all of them or not all of the tweets occupy a large part of mobile networks. So that's based on one of our previous work. From the right side of the figure, and we have find the log linear correlation between the Twitter data and the mobile traffic data. And then based on this correlation, firstly, we find that even though the uplink of Twitter app does not occupy a lot of the resource, but it is correlated. And secondly, even very little part of the users tweet, but we can't find this relation exists. That's what we use to big data to correlate with 3G traffic with this. So based on this correlation, we can achieve the high resolution because the coordinates are the points. Then we pre-process the data. As we said, firstly, we need to temporarily filter the data. For example, if we have 24 hours, we want to divide it into maybe 4 blocks, like morning, afternoon, evening, and midnight, because users' behaviors are similar in our experience in these different kind of categories, in which just like in the morning, users are going to the work, so they are on the transportation. And in the evening, they will go back to the home, so the traffic pattern should be similar. So the first one is to design a similarity function to find the similarity between each of the time of the point cloud and compare them, and then we can filter which period of time is similar with and different compared with others. So that's the first thing. What we did is to find two factors that can influence the similarity, just as the bottom left figure shows. We have pattern A and B1 and B2. It is clear that A is similar with B1 more than B2. Why is that? Because when we combine A and B1 together, let's see the combine together, and we can see they are close to each other. And A and B2, firstly, they are far away, and then the point number is different. They have different numbers. So that gives us two factors. The first one is distance of the coordinate points, and secondly, the number of points. That different factors give us a similarity. So we use these two factors to quantify the similarity. If the points difference are higher, so that they are less similar. And secondly, about spatial field theory, as we know that Twitter data is pretty noisy. Yeah, noisy. What we want to find, or what we need, or what we want to train is that data has high correlation with each other. For example, in one day, in Monday, Tuesday, it's the same of all the weekdays. So that we can use it to predict or generate if they are very similar. Like in the midnight, they're very light user, but in the rush hour, there are many users running everywhere. So that's a difference. We need to reduce some noise point to increase the similarity between different patterns. So that what we use is a density-based noise reduction called dbScan. I give you a reference under. It can give density, just a range, how many points are in this range, and to make other points, edge points or noise points, which doesn't include as many points as center nodes. And then it can reduce, mark them as a noise. That's its method. And this part is what we want to remain the hotspots in the data. So let's firstly see the result of the similarity of user distribution. That's a result when we run the temporal similarity. And along this side, it's a time of 2 weeks, 40 days of London, and that's the same. That's the same points. And we can see different blocks. Yes, and I mark with 1, 2, and 3. In the first here, that's a weekdays with weekdays. Yeah, weekdays with itself, weekdays with another week's weekdays. And then that's a weekends compared with weekdays, and weekends compared with weekends, weekends compared with another weekends. And I will briefly introduce what we find. Firstly, we can see that weekdays correlation is higher or more similar than weekends. Yeah, this block is disappear here. The higher similarity disappear. However, during the weekends, compared with weekends, it shows up as smaller. That means users becomes more random during the weekends. And during the weekends, maybe some are still at home, but some are still go outside. But during the weekdays, it is just scheduled with high correlation. And then we can find that 1 week compared with another week, like this one, there's also high similarity, but not as high as itself. And then what we can find in 1 day, that's 1 day, different hours in 1 day. First, this part, the block shows that during the nighttime. During nighttime, surely it's high, but because users sleeping. And this part is the daytime. Daytime, we didn't find like afternoon or something, just daytime, the working time of the daytime. And this one, evening time, yeah, after work. So what we did is to divide it into 3 blocks: the evening and on the work and after work. So that give us help us to filter the training data. And then we use a structure of GAN here, input the noisy and input the traffic, and use backpropagation to train the model. Yeah. And then sigmoid cross entropy TensorFlow and optimize it to do that. And then the performance of the generator, when we train along with the iterations. At the beginning, the generated orange points are very different, and along with the time dimension becomes similar, and then at around 300 iterations it becomes very similar of this one. There's some difference, but the distribution should be similar like this one. We don't want any points generated here, and that's the advantage. And it is just an automatic process, and it's amazing tool to use. And we compare with others when we use GAN generated in the daytime, evening, and also in the nighttime, and compare with snippets of stable, uniform, and normal distribution. We can see the similarity difference, and they're pretty low because there's no optimization of the parameters or how many distribution. So yeah, that's why advantage of GAN. And then what we can see, we have generated distribution of traits. This distribution coordinates of traits. What we need is a traffic. Yes. So we just transform into a matrix and use estimate correlation, what we find in our previous research, to transform spatial traffic pattern. And this pattern can be used to, deploy the simulation to deploy and mirror the difference. And in summary, we have designed an artificial cellular trap generator and achieved high-speed resolution and to see the day, evening, and night traffic. In the future, what we need to solve is firstly the training non-convergence and the testing other datasets. That's my presentation. Thank you, and I will upload this video to YouTube, and if you need questions, we can talk about it. Thank you.